Hello, Chem 110. I'm here to finish our discussion of thermochemistry. And to do this, we're going to look at standard elemental forms of atoms, talk about standard enthalpy of formations. We're going to talk about bond dissociation energy, and then review all of the tools that we have to determine the enthalpy of a given reaction. So this, of course, is our last lecture of new material for the semester. So congratulations on making it to here. And that means, of course, that Friday's live Zoom sessions will be going through a review session, a sort of quicker review. And so there won't be one of these videos and there won't be a lecture quiz for Friday. So let's go ahead and get into thermochemistry. So we're going to start by defining the standard states of the elements. So when we say standard states for an element, we're talking about a warm room kind of temperature, 298 Kelvin and 1 atm pressure. So if you were to kind of go out into the world with the standard temperature and pressure, how would you expect to find a given element if you're to go hunting for it in nature? And so we'll say that you would expect to find metals as solids. This makes sense when you think about maybe iron or gold. And we have our one exception that you guys probably all already know, and that is that mercury exists as a liquid in its standard state. Then we'll say the metalloids are also all solids. And then when we look at our nonmetals, we can predict that the noble gases, shockingly, are going to be gases in their standard state. And then we have the diatomics to keep track of. And so we've spent a lot of time with these already. We have our H2, N2, F2, O2, I2, Cl2, Br2. And we're going to get all three phases out of these diatomics. And so some of them will exist as gases in their standard states. That'll be hydrogen, nitrogen, oxygen, fluorine, and chlorine. And we'll have one that exists as a liquid in its standard state, which is bromine. And then we'll have iodine, which exists as a solid. And then that means that the rest of the nonmetals are left as solids. And so some of the solids can exist in different forms. And our sort of favorite example of this is when we talk about carbon. Because of course you probably have heard that pencil lead and diamonds are the same. They're both just carbon, but the carbons are bonded to each other in different arrays, resulting in all kinds of different properties. And so, not surprisingly, carbon's natural state is going to be in graphite, which is the pencil lead version. And so then some other examples are that sulfur exists in the rhombic state, and phosphorus exists as P4 in the solid white state. So don't stress about that too much for Chem 110, but if you go on to take a material science course, Penn State is one of the top material science institutions in the world, you can learn all about different structural arrangements of solids and how that affects the properties of those solids. And it's actually really interesting. Okay. So, more or less, if you can remember that pretty much everything exists as a solid. Mercury is weird. The noble gases are gases. And then the diatomics, you're good to go for the standard state of the elements. And so there is one tool we have to help us remember the diatomics and how they exist. And that is the expression, have no fear of ice-cold beverages. And so each of those words corresponds to one of these diatomic states. And then what we see here is that most of these are gases in their standard states. Iodine, which corresponds to the word ice, is a solid in its standard state. And beverages, corresponding to bromine, is liquid. So this expression can help you remember what these 7 diatomics are but then also help you remember which are our solid and liquid diatomics. And so we'll see how it can be useful in terms of thermochemistry to know what the standard states elements are in a moment. But before we address that, I want to introduce our third way to determine the delta H of a reaction. And that is through the standard enthalpy of formation for a given molecule. And so what this delta H of formation stands for is kind of if we were to make a molecule by adding together its individual elemental forms, how much energy would be, heat energy would be exchanged, given off or taken in. And excuse me, we can see an example of that down here where we have standard elemental carbon with standard elemental oxygen combining to form this molecule CO2. And the delta H for this reaction then tells us about the delta H for CO2. And so you might notice that this delta H has like a degree sign and the F there. And so this degree sign tells us something about the conditions our experiment was run under. And it's always going to be 1 atm and 298 Kelvin. And usually 1 molar if we're worrying about concentrations. And this value can be positive or negative. It just depends on the molecule that you're creating. And we can see a schematic of this reaction below, where we can see that carbon and oxygen on their own are at a higher enthalpy value than if we combine them to form CO2. And so then we can determine whether a reaction tells us about the delta H of formation for a given molecule by making sure it meets 2 criteria. And the first of which is that we only make 1 mole of product. And so if we look at our example reaction, we can see that the coefficient on our CO2 is just 1. Okay, so we're going to make sure we make 1 mole of product and that all reactants are in their most stable elemental form. Okay, and we can see that carbon's existing as a solid in its graphite form. So that's in its standard state. And then oxygen is O2 and it's a gas, so it's also in its standard state. So we need to make sure that both of these things are true in order to say that a reaction tells us about the delta H of formation for a given molecule. And so we can kind of keep thinking about this delta H of formation value. So it more or less describes how much energy is released to create a molecule from its components. And so this is just that same example. But then we can kind of consider about the importance of having elements in their standard elemental form for the reactants. And the reason that this is important is because we'll see that the delta H of formation for standard elemental components is 0. And that 0 is telling us that this is kind of the baseline that we would expect to find a given atom as. And then we can look at changing it away from that baseline. So there's no heat exchanged to form an atomic elemental state. And so what that means practically is that the delta H of formation for oxygen is 0 in its gaseous state. The delta H for I2 solid is going to be 0 because that's in the standard elemental state. And the delta H of formation for gold solid is going to be 0 because these are all in their standard states. And keeping this in mind will be useful for our next kind of equation that we're going to introduce. And our next equation is oftentimes referred to shorthand as products minus reactants, the products minus reactants rule. And it is a lot of like what it sounds like. So we have here the delta H for a given reaction is going to be equal to the delta H of formations of all the products added up, okay, times their coefficients, minus the delta H of formation of all of the reactants added up and times their coefficients. And so N and M are just there to represent the coefficients. Okay. And this sort of is an application of Hess's law, but you don't have to worry about connecting the derivation. And so usually at this point in 108 Forum, I would be really excited because we get to do one of the coolest demos of the whole class called thermite. Okay, and this is where we have to use a special kind of match for a reaction. We take this magnesium ribbon that's twisted all cool and set it on fire and then stick it in a flower pot, and the flame is so bright and white, and then you get sparks that just go everywhere as this reaction occurs. And they used to use it on railroad tracks, to kind of weld the rails into place. And so if you're curious, you can Google thermite reactions. It is very satisfying. And I'm sure if you go on to take other chemistry classes, they'll find an excuse to do thermite. Okay, so if we have this reaction, we want to figure out what the delta H reaction is. And I think I sort of just gave away that it's going to be exothermic. And so how we're going to approach it is to look up what the delta H of formation values are for the molecules in our reaction. And traditionally on an exam, we'll give these to you or give you some way to determine them. And so for the iron oxide, it's negative 824.2 kilojoules per mole. For aluminum oxide, it's negative 1,675.7 kilojoules per mole. And those are the values that you might be given on exam. And it might feel like something's missing, but you remember your standard elemental forms of atoms, and you'll recognize that the value for aluminum is just going to be 0. And the value for the solid iron is also going to be 0. And so now we're going to go ahead and set up our products minus reactants expression. So the enthalpy of our reaction will be equal to our products added together. So we'll have 1 mole coming from the coefficient of 1 in front of the aluminum oxide times its enthalpy of formation, and then plus 2 moles of iron times 0, which is its standard enthalpy of formation. And then we're going to subtract off our reactants. So we'll have 2 times the value for aluminum, and the 2 comes from the coefficient, which is again 0. And then we'll also subtract off then the value for iron. So we have our 1 mole from our coefficient of 1 here, times then its delta H of formation. And then we'll carefully plug this into our calculator, making sure that we're using our parentheses appropriately so that this negative sign gets distributed to both terms. And we'll see that our delta H reaction is negative 851.5 kilojoules. And that is exothermic because it's a negative value, which is what we would predict from a reaction that, shoots sparks and fire everywhere. So let's go ahead and look at another example. And so if we want to figure out the heat of formation for this reaction of formaldehyde with hydrogen gas to form methanol, we can again use our products minus reactants rule. And so go ahead and pause me and take a second to try to calculate this on your own. So 3, 2, 1, pause. Okay, welcome back. Thanks for pausing me and giving this problem an honest shot. Let's go ahead and solve it together. So we're going to do products minus reactants. And so I'm going to have an expression like this, where I have 1 mole from this one coefficient times the delta H of formation for the methanol, minus then the 1 mole from the formaldehyde times its delta H of formation. And I'm also going to subtract off the 1 mole of H2 times its delta H of formation. So when I plug in the values, I'll end up with an expression like this. Oh, I'm sorry that this says O2, it should say H2. Thank you for your patience. Okay. And so then when I plug in the values there, I'll remember to plug in 0 for the H2 since it is in its standard state. And then I can go ahead and carefully plug this into my calculator to solve for standard enthalpy change of negative 92.4 kilojoules. And so this reaction also ends up being exothermic. And if we were to put our hand up to the container where it is happening, we would feel it getting hot. And our thermometer would also feel it getting hot, and so we would see an increase in the temperature. So that is our products minus reactants rule. And so here I have another clicker question to kind of remind us of what we talked about at the beginning of the class with our standard states. Go ahead and take a second to pick which reaction has a delta H of formation equal to the delta H of the reaction. And if you need to, go ahead and pause me. Okay, good work on that question. Let's go ahead and look at what the correct answer is. Correct answer ends up being D. And if you were able to figure that out on your own, awesome. So let's go ahead and talk about why D is the right answer. So here we have our products minus reactants rule. And so for these two terms to be equal, we need this term to be equal to 0, which means we need all of our reactants to be in their standard elemental forms. And this also means that we need our coefficient on our product to be 1. And so if we look at answer choice D, we can see that N2 here is in its standard state, as is O2, so that checks out. And then we have a coefficient of 1 on our product, which is also good news. If we were to look at the other options then, so we'll circle this, you can see H2 gas is in its standard state, as is O2 gas. But here we make 2 moles of water. So the delta H of the reaction would end up being 2 times the delta H of formation for water. So that one's out. Okay. B is out because in our reactant side here, if you have a complex molecule like this, it's definitely not standard elemental form, so that one's out. The reverse might work, but not this version. And then here, this one is not for 2 different reasons. The H2 is good, but bromine beverages should be liquid in its standard elemental form. And then again, we should only be making 1 mole of product. And then for E, again, here we have a complex molecule as our reactant, so that's not going to be standard state. Okay, so that brings us to kind of our last topic of the semester, very last topic, which are bond dissociation energies. And we've referenced these before because we've talked about how single bonds generally will have a lower bond dissociation energy than double bonds due to having a smaller bond order. But the definition of bond dissociation energy is the enthalpy needed to break a bond for a molecule that's in the gas phase. And so breaking bonds is always going to require energy and be endothermic. We have to put in energy to pull two atoms apart. Whereas making bonds is always stabilizing. It's always exothermic and releases heat energy. And so there are some different ways that we get bond dissociation energies for different types of bonds and molecules. And so for the diatomics, it's nice and easy. We just think about taking one H2 and breaking it apart. And we end up getting this 436 kilojoules per mole for that. It's positive, of course, because breaking bonds requires an input. But then when you have more complicated molecules, even just as complicated as water, we have to kind of break the bonds individually. And so for water to remove the first hydrogen and to just break one bond requires 494 kilojoules per mole. But then to go ahead and break the second bond after we've broken the first requires a little less energy, actually. And so then, which energy is right? Which is the proper oxygen-hydrogen bond dissociation energy? The answer we kind of come to is both. And so we just average out those different bond dissociation energies. And so I bring this up just to keep in mind that bond dissociation energies aren't perfect, because the way we determine them might be, there might be little differences from the molecule we use to determine them from the actual molecule that we're looking at. They do give us a very good rough estimate. Okay, bringing us then to our fourth and final way to determine the enthalpy of a reaction. And it's going to be looking at how the bonds change between the products and the reactants. And so here we have this reaction of ethane with chlorine gas. And so what we can see is we're starting here. These are our initial reactants. And we can start by thinking about breaking this bond, the bond between the two carbons. And so that's going to be an input of energy. Now we're here, and we're going to break apart the two chlorines. And so now we're here. And then now what we're going to do is add these chlorines on to each of these CH3s to give us two CH3Cls. And forming bonds is going to be stabilizing, it's going to decrease the energy. And so then if these are our reactants, we can see here we have our products. The overall enthalpy change then will be from products minus reactants. Okay. And so then we can see that we're going from a higher energy level to a lower energy level. So we do expect our delta H value to end up being negative for this reaction. And so this is one way to kind of sketch out what's going on, a way to kind of, take your reaction that's written here and turn it into sort of picture or map. And we can kind of convert this idea into another sort of equation where we say that the enthalpy change of the reaction is going to be equal to the bond dissociation energy for a given type of bond, times how many bonds of that flavor we have, minus how much energy is given off by the bonds that are formed. So it's going to be bonds broken minus bonds formed for a new rule. And so we can go ahead and look at an example of this where we have hydrogen peroxide decomposing into water and oxygen. And here they give us bond dissociation energies for a whole bunch of different bonds. And how can you really talk about bonds changing without drawing the bonds? And so our first step is always going to be to draw out the structures. So here I have my 2 hydrogen peroxides, and then I have my 2 waters and my 1 oxygen. And so I can kind of keep inventory of what I have. So here I have my different types of bonds. So on the left, I'm going to have 2 oxygen-oxygen single bonds. And on the right, I have 0. So that means I must have broken 2 oxygen-oxygen single bonds. And now I can look at oxygen-oxygen double bonds. And I don't have any on the left, but I do have 1 on the right in that O2 gas. So I must have made 1. Then next, I can look at my oxygen-hydrogen bonds. And on the left, I have 4. And on the right, I have 4. So no change, nothing happened in terms of those bonds. And then I can look to see if I have any hydrogen-hydrogen bonds. So I have none on the left and none on the right. So we're not going to use that value. So now that I know how my molecules have changed, I can go ahead and start to set up my bonds broken minus bonds formed. And so I'm going to have my 2 oxygen-oxygen single bonds times that bond dissociation energy from the table, minus then my 1 oxygen-oxygen double bond that's formed times its bond dissociation energy. Okay. So if we go ahead and put some numbers to this, we'll have our 2 bonds times this bond dissociation energy here, minus our 1 bond times its bond dissociation energy from up here on the table. And we end up calculating a delta H of reaction of negative 203 kilojoules. And so, what we can do is write this number in terms of how many moles of H2O2 are present. And so what we're going to have to do is say this is, applied to the whole reaction. But in that whole reaction, we have 2 moles of hydrogen peroxide going in. And so to write it in terms of hydrogen peroxide, we're just going to have to divide by those 2 moles. And we get a bond dissociation energy per mole of H2O2 is about negative 102 kilojoules. And the only reason I wrote it like this is just because it's how it was specified above. Okay. So let's go ahead and take a look at another example. And I guess before we do that, we can kind of recognize how this value that we calculated per mole of H2O2 is slightly different from the published value, but it's pretty close. So I'd say that with bond dissociation energies, you can really make a good estimate. Okay, so here we have an example with nitriles, like acetonitrile, reacting with a palladium catalyst and hydrogen to make this ethylamine. And we have a bunch of bond dissociation energies in that table. We're going to try to figure out what the delta H of the reaction is using those terms. Okay. So I really do want you guys to try doing this. So please go ahead and pause me. Okay, good job. I hope you were all able to get the setup started. It helps that you're given the structures already sort of to go for this reaction. Let's go ahead and work through it. So we have our acetonitrile and our 2 hydrogens. And now everything is drawn out explicitly. And so we know we're going to use our bonds broken minus bonds formed rule. Okay, so we can keep track of what broke. So we can see the carbon nitrogen triple bond broke. It's there on the left, but not the right. There's no hydrogen-hydrogen bonds on the right. Those are both breaking. But then we can see we have some new bonds. There we have carbon-hydrogen bonds that we didn't have before. Here we have the carbon-nitrogen bond that's now a single bond, so we're making a new connection between those. And then we have some new nitrogen-hydrogen bonds. Okay. And so we can kind of write out this expression where we say we have one carbon-nitrogen triple bond breaking, two hydrogen-hydrogen bonds breaking. And always feel free to make a chart for yourself where you're kind of tallying what was broken and what was formed. Make sure you include everything in your calculations. So we have those bonds breaking. And then we're going to subtract off the bonds that are forming. So we have our carbon-hydrogen bonds here, our nitrogen-hydrogen bonds here, and then our one carbon-nitrogen single bond now that's forming. And so then we'll just plug in the values in kilojoules given from this table, making sure we're being really careful that we pull the right numbers. And also being okay if we don't use some of these values, that's okay. So then we will get a delta H of reaction that is equal to 1763 kilojoules from our bonds that are broken, minus 1901 kilojoules from our bonds that are formed, giving us a delta H of reaction that's about 138 kilojoules released. Okay, so it's an exothermic process. Heat is going to exit the reaction. And so again, we will feel it getting hotter and see an increase in temperature. And so that brings us to the end of our 4 ways to determine the delta H of a reaction. And so the first way we talked about was Hess's law. The second way was through calorimetry experiments. And then today we start talking about using the standard enthalpy of formations and using our products minus reactants rule. And then finally using bond dissociation energies and looking at what bonds are broken and what bonds are formed. So make sure you're comfortable with each 4 of these tools, because we'll expect you to be able to, apply any number of these. And so with that, I want to say thank you to all of you. This semester certainly didn't go the way that we had hoped when it started, but it really has been an honor for us to work with you. And I think I can speak for Dr. Bojan and Todd also when I say that. And so thank you for being adaptable students who are driven and independent and hard workers. And I wish that we could have spent the whole semester together and continued to get to know each other and work more closely together. But I'm grateful to be able to be here with you through the screen. So thank you. Have a great finals week, and I hope that you're able to finish the semester strong. Take care. It's getting cold, and as with the thermometer telling us that we should expect a decrease in temperature when this reaction happens. Oh, shoot. I messed up. Not a ton, but a little bit. Okay, this is fine.